So yesterday was sine and cosine. Today we're going to look at the other trig functions and what we can do with those. So we will have some time today at the end to go over questions on homework again like yesterday. So we should be able to go over some of those questions if you had any from yesterday's homework. So you can stick around and ask me some questions on those. So let's kind of pick up where we left off. And we're going to look at now trig functions that have to do with tangent and secant. So that's the main thing we're going to look at now is tangent and secant, but also we'll mix in there some cosecants and cotangents. But there is some nice relationships between tangent and secant. So let's write a couple of them down. We've already maybe written some of them in terms of integrals, but we'll write a couple of the other ones you should know down. So a couple of the Pythagorean identities. Do you know what 1 plus tangent squared equals? Secant squared, right? So this identity could be used to replace like tangent squared with secant squared or secant squared with tangent squared. So if we wanted to replace one with the other, we could do that using this. We also have the other Pythagorean identity is 1 plus the cotangent squared. Do you remember what that equals? That's the cosecant squared. So this relationship could be used to replace like cosecant with cotangent squared or vice versa. So remember, anytime we wanted to replace sine squared with cosine squared, we used that Pythagorean identity, that sine squared plus cosine squared equals 1. So these we can use to replace one of these with the other as well. The other thing you should know is kind of the relationship between tangent and secant and their derivatives. So I'll just remind you of those. Just a reminder that the derivative of the tangent, what's the derivative of the tangent? Secant squared. And that's something we'd probably want to watch for if we are going to do some sort of substitution. Like if we let u be tangent, then I better have some sort of secant squared showing up. Or, what's the derivative of secant? Secant tangent. So if I'm going to let like u be secant, then I'd want to be watching for a secant tangent to show up in my integral so I could use that as a du. So if I'm going to make some sort of u substitution with these, I'd want to make sure these du's are possibly showing up. I'll also mention the ones just for cosecant and cotangent as a reminder. We don't see these functions as often, but it's good to write them down. What's the derivative of cosecant? Cosecant, cotangent, and these have negatives on them. That's why I always remember these other odd ones at the end. These have negatives, so that one becomes negative cosecant, cotangent, and the derivative of cotangent is negative cosecant squared. Got it. So negative cosecant squared. So also, something to watch out for if you're doing some sort of substitution, you let u be this, you want to have that du to kind of show up in there somewhere. So those are a couple of things just to remind yourselves of. These are the main identities we use, but then also these relationships between the derivatives and what you end up with there. So we're going to go through some that have now products of tangents and secants, or some products of these trig functions here. And so we're going to see, using kind of some similar techniques to yesterday, how we might be able to integrate these. So let's start with this first one here. We're going to integrate tangent times the secant cubed of x. Okay, so tangent times secant cubed of x. All right. Where should I even begin? Okay. What do you think? Any thoughts? u be secant? Okay, if we let u be secant, what would we need for its derivative? Okay, so he's saying, what if we let u be one of these, like secant? So let's think about this. So if u is secant of x, the derivative, that's what he was saying, is secant x tangent x, right? Could I have that in this integral? Do I have it here? Yeah, if I separate a secant out, right? So let's do that. Let's do a little separation here. So I'm going to separate out a secant of x, and then I'd have a secant squared left. And if I do that, then I see there's my du, the tangent secant, and u being secant would just become now u squared. So that seems like a pretty good strategy. So when I had this odd power, I could separate one out, so I had both the tangent and the secant, and the derivative shows up. So let's go ahead and substitute now. So all of this that I've underlined becomes the du, right? That's all du. What do I replace this with? Secant squared. U squared, right? u squared du. So, can I integrate that? Yeah. How do you integrate u squared? Yeah, 1/3 u cubed, right? Or u cubed over 3. No problem. So once I put it in that form, not too bad to integrate. So then I put the u back in, I get 1/3 secant cubed of x plus c. So here's a good place for us to kind of use that relationship between secant and its derivative that's showing up here, the secant and the tangent. Okay. So that seemed to be a pretty good choice in that one. Let's see what might be a good choice in the next one here. Now this one we have secant to the 6th and tangent to the 6th of theta. And notice this one has some limits. We'll just deal with those at the end, but those are from 0 to pi over 4. Okay, so we still have secants and tangents. What do you want to do with this one? Any thoughts? Yeah, we can. And you're thinking maybe let u be tangent. Why would you want to let u be tangent here? Right, because the derivative is secant squared, and here we have an even power, right? So I don't necessarily want to separate out, like in the last one, a secant tangent, because then I'm left with odd powers, like to the 5th. And I can't do a lot with odd powers, like I can't use Pythagorean identities to substitute. So it's usually better if I can left over an even power. So let's try that and see how this would help us. So we're saying maybe let u be tangent theta, and then du would be secant squared theta. And I could definitely separate that out of the secant to the 6th, right? So I'll start by doing that. I'm going to separate these a minute. So I'd have secant to the 4th theta, tangent to the 6th theta, and I'll just separate that secant squared over here with the d theta. So I know that's going to be my du. So that wouldn't be too bad, because here I see that's going to be the du, right? The tangent I could substitute. That's our u, so that'd be u to the 6th. But what am I going to do with these leftover secant to the 4th? Because they're not u, right? And I don't want to have any more than I have for du. And they're not tangents. What did I do when I had leftover sines and cosines and I wanted to replace the other one? Power reducing, we can use it. Unfortunately, we don't have power reducing for secant. We only have it for sine and cosine. Okay, so we have an identity though, right? So remember what the identity is? What is it? 1 plus tangent squared equals secant squared? So I can switch any secants that are to an even power anyway into tangents. So if I can replace everything else and put it in terms of tangent, great, because then I have it in terms of u. So let's go ahead and do that. So secant to the 4th, we can rewrite that as, right, secant squared squared. So now I can replace that. What can I replace the secant squared with? 1 plus tangent. So it just becomes 1 plus tangent squared all squared. Okay, so that's kind of what we did right with sines and cosines. Sometimes we would save one out that was the derivative, and the rest we would try to put it in terms of u. And so if there were secants left, we'd try to put it in terms of tangents. So we could do that with that identity. So now we should be able to substitute. Remember, all this is du, this is a u, and here's another u. So now I should be able to write everything in terms of u. So I'll have 0 to pi over 4. 1 plus u squared squared, right? U to the 6th and a du. So remember, tangent's the u, so this one's u squared, but it's still squared. This will be u to the 6th, and all of this is our du. The other thing is we could change the limits, right, as well when we do a u substitution here. So if you want, we could change the limits here, and then we don't have to go back to theta. Do you want to change limits? Sure. Okay, so let's do that. So let's see, if our theta is 0 and pi over 4, what would our u values be? So let's see. So if theta is 0, what's the tangent at 0? 0. I like that one. And what if theta is pi over 4? What's the tangent at pi over 4? 1. Yep. So that's 0 and 1 actually, so that will be pretty easy. So I'll change my limits here to 0 and 1. Okay, so question is, how are we going to integrate this? Can I integrate it? Yeah, sure. We saw some of this yesterday, right? What do I got to do first? Foil this, right? So foil this out, square it out, and then distribute the sixth, right? Okay. So let's go and foil that out. I should get, what, 1 plus 2u squared, good, plus u to the 4th. Okay. And then go ahead and distribute the u to the 6th then. So that'll be u to the 6th plus 2u to the 8th plus u to the 10th powers du. Alright, and then we just need to integrate that. I don't know if I got to the back yesterday, so let me start back there. David, what would you get if you integrated that? Good? Yeah. Exactly. No plus c because there's limits, so there we have our integration. So it's 1/7 u to the 7th, 2/9 u to the 9th, 1/11 u to the 11th plus c. No, we just said no limit. 0 to 1. I always want to try plus c myself. Okay, so this shouldn't be too hard to plug in these limits. So if we plug in 1, you basically just get the fractions, right? So you got 1/7 plus 2/9 plus 1/11. What will I get when I plug in 0? 0, right? So all of these will be 0, 0, 0. So the rest of those are 0. So I basically just need to add those fractions together. And you can use your calculator to help you. So I brought my calculator here. Let's see what we get. And just make sure you keep it in fraction form. You usually don't want the decimal form. So keep it as a fraction. We usually like to stick with exact forms. So let's see what we got. My answer is a fraction. I got 316 over 693. Not exactly obvious, but you can also get a common denominator and get it that way. But that's what the final answer will be there. Good? Okay. Awesome. So let's kind of summarize a little bit what we've seen in these two cases with tangent and secant. So notice what happened in this one when we had an even power. So we had even power of secant, and so we really wanted to separate then out a secant squared as our du. So that's usually what happens there. Now in the first one, we had an odd power on secant. So there it was better to actually separate out a secant tangent so that we're left with an even power. So that tends to be what we do here when we're working with tangents and secant. So let me kind of summarize that here. Strategy for those. So if the power of secant is even, that's usually when we're going to save a secant squared x factor. For kind of your du. So you're going to save a secant squared x factor for your du, and then express everything else in terms of tangent. That will be the best strategy there. If we can express everything in tangent, you may use that identity, 1 plus tangent squared equals secant squared. But that's your goal, because then your u will be the tangent and your du will be that secant squared. Okay, so I'll just make a note here. Remember, you can use the identity here, 1 plus tangent squared equals secant squared. Okay, so that's kind of like part B we did in the last example. So if we have an even power secant, we're going to save out that secant squared. Anything else we have left, we could rewrite as tangents and then do a substitution. Now, if the power of tangent is odd, and sometimes secant as well, this is where you're going to save out the secant tangent factor. So you would save out a secant x tangent factor and then express everything else in terms of secant. And you could use, you can also use the identity if you need to. We didn't really need to in part A, but if there were any other tangents, we could use that identity to actually write them in terms of secant. We could use this identity, that tangent squared equals secant squared minus 1. Same identity, just solve for tangent to write it in terms of secant. So if there were tangents left over, you could replace them with secants and then do the substitution. So here u would be secant, and the du you've left out is the secant tangent. So those are some guidelines there. Again, that's for integrals in this form where you have some tangent to a power times secant to a power. That will be the best strategy to use on those. So you'll see a couple of those in your homework today with tangents and secants. So you can use those to help you with that. Okay, the last couple examples I want to show you aren't necessarily specific strategies we've got to use. They're just trig functions. We may use some identities we've already talked about for sine, cosine, or tangent, secant. The guidelines aren't necessarily clear-cut on these. We just got to look if there's an identity or some substitution we could use that would really help us here be able to integrate them. So let's look at a couple last examples and see if you see some strategies that might work here. So here's the integral of d theta over 1 plus cosine of 2 theta. Okay, so as this is, it would be difficult to integrate this. There's a cosine of 2 theta here, but I don't see, like if I let this be u, that there's a sine for my du. So that might be difficult to do as it is. So I might be thinking, what here? Any ideas? Okay, some identity, right? What do we know about cosine of 2 theta? What is it equal to? This is the one that has lots of options, right? Cosine squared minus sine squared. That's one option. What else? 2 cosine squared theta minus 1, right? Or 1 minus 2 sine squared. Okay. So I have some options here. So let's think about which of these options will work best in the denominator on this one. I don't really love this one, because then I have 1 plus cosine squared minus sine squared. I don't really know if that's going to help me simplify it at all. What about the second one? You like that one at all? Why do you like the second? I like getting rid of 1, right? That should make it simpler. And that way, if I have 1 minus that 1, those could cancel. So let's try that and see if it makes a difference here. So we do like things to simplify. So if we can get those 1's to cancel out, that would be great. So I'm going to replace cosine with 2 theta with 2 cosine squared theta minus 1. And then, as Benham said, the 1's would cancel. And so now I just have d theta over 2 cosine squared theta. Okay, is that going to be helpful? Possibly. What's this 2? What can we do with this 2? We could just pull it out as 1/2, right? That's just a constant. Now what can we do with d theta over cosine squared? What's 1 over cosine squared? That's a secant, right? So I could just write that as secant squared then, right? D theta. And wait a minute, didn't we just talk about what's the integral of secant squared? Where does it come from? Tangent. So if I could write as secant squared, that's really easy to integrate. That's just tangent. And I'm done. So just using identity here and simplifying a bit, I get something that's really easy to integrate. That's the integral of secant squared is tangent. Put on my plus c, and I'm good to go. Okay, so sometimes just a matter of, is there an identity I can use to hopefully simplify? And again, this was a good choice. So this one has 3 options, but I like it when things cancel out, makes it a little simpler. Then I don't have more than one term in the denominator. Okay, so there's a case where we just use an identity. So let's check out B, what I would do in this one. So this one has the square root of tangent x, and then secant to the 4th of x dx. Okay, so the square root of tangent x and secant to the 4th of x. Now this one is actually similar to the last couple ones we did, right? It's tangents and secants. So we're kind of dealing with the relationship between tangent and secant. What should I do here? What can you rewrite a square root as? Yeah, to the 1/2. So maybe that's helpful to think of. Sometimes the square root throws students off, but it's really just another power. You can even write it in here as 1/2 if you like that notation, but it's just like another power, like 4th. It has the power of 1/2. So what do we know about this one? What should we do if we have tangents times secants? Yeah, why? Because what's the power on secant here? It's in what type of power? Even. So if you have an even power on secant, you usually want to separate out a secant squared and let that be our du. So that's what I'm going to do here. So let's try that. So we're going to separate out a secant squared. So I'm left with secant squared x. And so what I'm hoping to do is let u be tangent so that the du then can be that secant squared x part, so that this is all the du. But in order for me to do that, what am I going to have to switch? I see a tangent here, but what am I going to have to change? I got to rewrite another one, right? Yeah, the middle one, right? I can't leave this. This is all part of du, but I want to replace the rest. I want them to be tangents, so I can write them as u's. How can I replace secant squared? 1 plus, what's the relationship? 1 plus tangent squared, right? Yeah, so I can substitute secant with a 1 plus tangent squared. Replace that, and then I should be able to do this u substitution, right? Okay, so I have tan x to the 1/2, 1 plus tangent squared, that's what I replaced the secant squared with. And I know all this is kind of matching up to that du there. So what's it going to look like when I replace it? Let me go to Michael. What's that going to look like when I replace it? What will it be in terms of u? Good? Du, perfect. So this is the u to the 1/2, 1 plus this is u squared, and then a du. Right? So here's my du, this is u, and that's u. Okay, so now I have u to the 1/2 times 1 plus u squared du. Jim, what am I going to do to integrate this? What do I got to do? Yeah, distribute on this one. So this just has a u to the 1/2 we need to distribute through. So that'll be u to the 1/2 plus u to the, what's u to the 1/2 times u squared? Yeah, 2 plus a half is 5 halves, or 2.5, right? So this is 4 halves and 1/2 is 5 halves. Good. Good, that's exactly right. So now we just need to integrate this. So u to the 1/2 plus u to the 5 halves du. So let's see what we get when we integrate. Jeff, what are we going to get here? What the new powers will be? Good. Very good. Yep. That's exactly right. So add 1 here will give you 3 halves and multiply by the reciprocal. Add 1 there will give you 7 halves multiplied by the reciprocal. We've got our plus c. There's no limits on this one that I forgot, right? Okay. So there's a plus c on this one. Anything else we should do? Yeah, put back in what? What's our u? Tangent. Yep. So we have 2/3 tangent of x to the 3 halves plus 2/7 tangent x to the 7 halves plus c. Good. So this one looks a little bit different with that square. square root on it. But remember, that's just a power. And so really what we're dealing here with is just products of tangents and secants. So we can use some of those guidelines we looked at today, where when secant has this even power, that's usually where we're going to separate out secant squared x and make that our du. Okay, questions on that one? Okay, there? Okay, let's do one more here. This one has cotangent squared in it. So let's see what we can do with that one. So this one does have limits, so don't let me forget those at the end. This one goes from pi over 6 to pi over 2, and we're doing cotangent squared of x dx. Okay. There's not an integral of cotangent squared, is there? I don't think so. There's like a cotangent cosecant or a cosecant squared. Those have integrals, so what should I do with cotangent squared? Do we know anything about cotangent squared? What kind of things? Okay, so there's an identity that involves cotangent squared. Let's write it down. So it was 1 plus the cotangent equals cosecant squared, right? So we could replace cotangent squared with cosecant squared x minus 1, as Taylor said. Okay, so let's do that and see if that gets us any closer to being able to integrate. So we have the integral from pi over 6 to pi over 2. We're going to replace this with the cosecant squared of x minus 1. Is that going to be helpful? Why? Right. Don't we know where cosecant squared comes from? Where did it come from? It's the derivative of what? The cotangent, and we can easily also integrate 1. So I should be able to integrate both of these. So remember, the derivative of cotangent is negative cosecant, so what's its integral? Negative cotangent, right? Yep. So that should be negative cotangent x. What else do I need? What do I get from the minus 1? Minus x. And I'm not going to put on plus c this time. I'm going to put on the limits. From pi over 6 to pi over, it was 2, right? Yeah, pi over 2. Okay, so let's see if we know the cotangent of these values. Alright, so we're going to start with negative cotangent of pi over 2 minus pi over 2, and then minus negative cotangent pi over 6 minus pi over 6. Okay, let's see if we can do it. What's the cotangent at pi over 2? Yeah, pi over 2, the point is 0, 1, right? And the cotangent is the x over the y, 0 over 1, so that should be 0. I was thinking unit circle, so that should be 0. What's the cotangent at pi over 6? It's the x over the y. Yeah, it's actually 1/2 over the square root of 3 over 2. Is that right? So I'm just thinking on the unit circle at pi over 6, what's the point? Square root 3 over 2, and then 1/2. So if we divide those out, what do we get? Square root of 3? Okay, so what do we got? Negative pi over 2. These two negatives make it plus square root of 3, and that makes a plus pi over 6, right? So I might not do too much, but I could add these pi's together. I will simplify it a little bit. So let's see what we have here. Square root of 3, what's negative pi over 2 plus pi over 6? So that's negative 3, 6 plus 1, 6, negative 2, 6, or negative pi over 3? Yeah. So these are 3, 6 plus 1, 6 is negative 2, 6, which makes a negative pi over 3. That's a good call. I don't know. Maybe 0.1. If you do have like terms, we try to add them. I never actually usually want it where you have like, if they're fractions necessarily, and one's pi and one isn't, that you have to make an entire fraction out of these two. But usually if they have pi's, I would want you to add those together. So, yeah. So try to simplify if you can. But this, I wouldn't necessarily require you getting a common denominator. So. All right, so this one, again, sometimes you just got to think, do I know any identity that might help me? If I can't integrate it as it is, can I make a replacement for it that maybe then I can integrate? So be looking for those. Look for identities you might be able to use, or like in B where you could do a U substitution. That happens a lot when you have products of two different trig functions that you would want to try to do a U substitution. So I think that's it for today. Yeah, a little shorter section. But we're going to leave some time. I'll send around the attendance, and I'll just leave some time. We can go over some questions if you have any on the homework from yesterday. So today's the 27th, right? Yes. It is? Okay, good. Okay, so let me send this around. If you don't have any questions, like you totally got the last homework, feel free to just leave it and you're free to go after you signed attendance. But otherwise, I'll go over some questions on the homework. Let me get it out here a minute and we'll look at some. So, yeah. Oh, yeah. This one? What happened? Was this one? This is positive, right? And that was negative? Negative 3 plus 1. Isn't that negative 2? That's what you're asking right here? How do these two combine? So you have negative 3 6 plus 1 6 leaves you with negative 2 6. And that should reduce to pi over 3. Yep. Yeah, I just reduced it. I didn't show that part. But it is negative 2 6 or negative pi over 3. Okay, anything from the homework? What should we look at? 10? Is that the most popular one? Okay. Okay. Oh, sure. Yeah, let me briefly talk about that, and then we'll do number 10. I do think 10 was one of the more challenging ones. So 56, when it says to explain the different appearances of the answers, well, yesterday we kind of talked about how sometimes you get different answers, but they're actually equal, right? And so you might say, or you might either show, like how one equals the other, and maybe how they only differ by a constant. So whatever your solutions were in 56, were they pretty close? Some of them were actually the exact same, weren't they? So do we show this back? You could write it out and do any work. Like I think B and D were exactly the same, right? So it's mainly how does it relate to A and C. So maybe try an identity to go from B to A to show that those are equal. Yeah, show like, here's this. Yep, and when I replace this, I get this, and so the only difference is a constant, or whatever it is. Yep. Yep. Okay, so let's look at number 10. 10. Am I looking at the right one? Is it from 0 to pi, sine squared, cosine to the 4th? Okay. 0 to, okay. Oh yeah, this one probably took the most work. Because what happens when they're both even like this? What do you have to use here? Power reducing, like a bunch of times. So that's why it's kind of messy, right? So you basically have to do power reducing on all of these. Like the sine squared, you can split this up into cosine squared, and use the power reducing on all three of them. And then you might have to do it again. So it might get a little crazy, but let's see what happens. So did you do power reducing here? This is 1/2, 1 minus cosine 2x, right? I think the hard thing for me was keeping track of like the fractions out front. But let's see what happens. This is 1/2, 1 plus cosine 2x, and so is this one. Oops, are they t's? I gotta go back to t. Sorry, those were t's. I know, I don't know. They just always did x. It'd be awesome. Okay, so those are all t's. So I just power reduce each of these. And then it's mainly you gotta just multiply this together. So is it gonna get easier or was it ugly? Well, I'll do the first two at least. Those aren't too bad, are they? 1/2 times 1/2 is a 4th. I'll pull that out, and actually maybe I could pull all 1/2s out and they can be an 1/8. How about that? So when I FOIL this, I get 1 minus 2 cosine of 2t plus cosine squared of 2t. Yeah? Oh no, those will cancel, won't they? So this will be a minus as well. I forgot that was a minus. So 1 minus cosine squared of 2t. I feel a little nervous about distributing the rest of this out. You know why? Right. Because it becomes it's going to be cosine cubed, right? And then it's like, what are you going to do with cosine cubed? But really, is there anything else we could do here? I mean, there is an identity here, isn't there? Sine squared, right? 1 minus cosine squared of 2t could be sine squared of 2t. But I'm not sure if that will help me, because if I would still have to distribute. Yeah. And you can get there. Maybe let's do it. Why not? So, we'll replace this with sine squared. That's what you did? Or no, you distributed those two. Did you distribute sine squared? Oh, okay. Well, I'm going to do it like this, and we'll see what fun we have. And we can probably get to the same answer, but I'm going to go ahead and distribute this through, so I'd have a sine squared plus a sine squared of 2t cosine of 2t. And yes, this might not be the only way to solve it, but we should get the same answer in the end. Fingers crossed. The nice thing about distributing now is I can kind of integrate these separately. So that's kind of nice. Actually, this piece wouldn't be hard to do with the substitution, right? Because here's a u is the sine and there's the du is the cosine. So that part won't be hard to integrate. What could I do to integrate a sine squared? Yeah, you'd probably have to do another power reducing, right? But I can, and that's not hard to do. So I could split this up now and just do two things. The one I could do by substitution, and the other one, this one, I could do by power reducing. So I'm just going to separate them into the two integrals. And so on this one, I could let u be the sine of 2t, because then the cosine, the derivative of that is there. And technically, it will have a 2 with it, right? Because you're going to multiply by the derivative of the inside. So I'll have to adjust with the 1/2 out front to match up to that. So I'll kind of finish on the right here first, and then we'll go back to this one. So I'll have 1/8 the integral of, there's my u squared, and a du, and I'll need another 1/2 out front. So I'll basically end up with 1/16 u to the third over 3. That looks crazy. 1/48 sine cubed of 2t. Okay, and I will go ahead and put the limits here in a minute. I'll wait until I get the other piece and apply it to both of them. Okay, so then we'll evaluate that from 0 to pi, which hopefully won't be too bad. And actually, you could plug them in here and just add that to your other answer. So I'll come back to that one. Let's go ahead and integrate this one. So this is where we'll do another power reducing. So remember, we can replace sine squared with 1/2, 1... Is it minus or the plus? Sine squared is the minus, yep. Cosine of, what's it going to be inside if it's already 2t? 4t, yep. So that becomes 4t. And then we can integrate this. So I'll pull this out front to be 1/16. And then I just have the 1 minus cosine of 4t, and that shouldn't be too hard to integrate. So I'll have 1/16, looks like that integrates to a t. What does the cosine integrate to? Sine, right? And I'll have to divide it by 4. So 1/4 sine of 4t. And then from 0 to pi. Yeah, those are good times. Okay, so that's really kind of your pieces to it. And then if you want to just plug in both limits, kind of simplify. I'm hoping things become 0 a lot, but we'll see here. They do, right? Okay. So in this one, we'd have 1/16. We'd have 0 minus sine at 0 is 0. Oh no, pi first, sorry. Pi. Pi goes in first, minus sine at 4 pi, though that is 0. So this one's pi. Plug that in. Minus 1/4 sine at 4 pi, which is 0. And plug in 0, and the sine at 0 is 0. So from this one, all I'm getting is pi over 16. Pi and 1/16. Let's go to this one. So this one I'd have 1/48 sine cubed at 2 pi. That's 0, right? Sine at 2 pi is 0. And what is it when you plug in 0? 0. Hallelujah, lots of zeros. Okay. So what do I have left? Only the pi 16ths. If you got that, you were right. And again, I kind of split mine up into 2. I did that change from 1 minus cosine squared to sine squared. You guys filled it out. Did you get the same answer? See, it could also work that way. So, was it? Did it get pretty ugly when you did it here? So you like foiled this out and got like cosine cubed. So you probably have to split that up into cosine squared and cosine, then power reduce again. Ooh, yeah, okay. So that actually makes me glad I didn't go that direction. Stop myself before I went too far. Alright, good. Yeah, it does. Just maybe it's a little longer, so. What else? Any other ones you want to look at from yesterday's homework? Sure. Number 9, sure, what was that one about? It looks easy but threw you off. This is another one where you have to use power reducing a couple times. So yeah, we can look at number 9. I'll do that one. As I said, if you don't have other questions, feel free to leave whenever you're ready here. We're just going over homework. So let me do number 9. Okay, so 9 from 7.2. This is the integral from 0 to pi. Cosine to the 4th of 2t. Okay. So this, yeah, when it's an even power, you're probably just going to have to do power reducing. So I'm going to split this up into cosine squared and cosine squared. And apply the power reducing to both of them. So I apply it to this one and FOIL that out. So this is 1/2 1 plus cosine of, what's that going to be? 4t, right? It doubles it. So when you do the power reducing, you got to double that to 4t. And same on the other one. Okay, so now do you see what to do? So pull out the 1/2, make them a 4th out front. FOIL these two out. So then you'll have 1 plus 2 cosine of the 4t, if you add the middle terms together, and cosine squared of 4t. They're both positive. Cosines are both positive in the power reducing. Anything else I could do now? I can integrate this, and I can integrate that. What's the only thing I still can't integrate? Square. What are you going to have to do with that? Power reducing. Yeah, change it again. So now this time it'll be 1 plus 2 cosine 4t, and that will become 1/2 1 plus cosine of how many t now? 8t. So that will be now an 8t. So now I should be able to integrate all these pieces. You probably want to distribute this 1/2 through. And in fact, what could you add the 1/2 to in here? This is 1/2 plus, nope, because that's out front being multiplied. But there is a 1 right here. So you can add together this 1/2 and the 1. You don't have to, but if you want, that would simplify to 3 halves. So if I add this 1 and this half, that goes to 3 halves. Okay? And then you have 2 cosine of 4t. And don't forget this half applies here to the cosine of 8t. So yeah, this half can't come out front with the 1/4 unless you can factor out of everything. So it's really just a term that can be added together with the 1, but not taken out front because it's not a factor. And then we can go ahead and integrate. So what would we get here? Oh, let me rewrite this. Yep, 3 halves t plus, no, yeah, plus, well, the integral cosine is sine, right? Positive, right? So it'd be 2 sine of 4t, but you would divide it by 4, yeah. Plus, this is also a sine, right? So 1/2 sine of 8t, but you got to divide it by 8, exactly. So 1/16. And then plug in 0 to pi. So this is what we were talking about, Austin, right? But I didn't have the 2t inside. I just did it for t. Is this the one? Is that the one you asked me about? I think so. I can't remember, on the blue paper. But I don't think I knew that was 2t, so that might have changed our numbers inside. I can't remember. So anyway, follow this one. So yeah, what do we got? So we've got 1/4, I'm just going to rewrite this a little bit. 3 halves t plus 1/2 sine of 4t plus 1/16 sine of 8t. So then plug all that in. Yeah. Yeah, but pi's are going to make all those 0 and the 0 as well, right? So yeah, so basically all you're going to get is times the pi. So 1/4 times 3 halves pi, the rest is 0. So what is it, 3 pi over 8? Okay, awesome. Yep. Yeah, all the rest of those will be zeros when you plug in pi and 0, so nothing to worry about there. Okay.